Hello everyone, this video is on one of the important properties of group homomorphism. It states, let phi from G to G dash be a group homomorphism and H be kernel of phi and A be any element of G, then phi inverse phi A equals to the left coset AH that equals to the right coset HA. Now I'll explain what this theorem means. By group homomorphism, the identity element of G must map with the identity element of G dash. So the image of E is E dash that equals to phi E. Let us suppose the other elements of G that has image phi E are H1 and H2. That means suppose H1 and H2 also maps with phi E. Then in this case H that is kernel phi becomes H1 E H2. H1 E H2, these elements are the kernel phi. Now we know A maps with phi A, so phi inverse phi A are those elements of G that maps with phi A, and by the theorem phi inverse phi A equals to AS that equals to this set. So the elements of G that maps with phi A are these elements AH1, A and AH2 by the theorem. So what this theorem means is that if these are the elements that maps with phi E, that is if these are the kernel phi, then the elements of G that maps with phi A are these elements, that is the set AH and that equals to the set HA. Next we proceed to the proof. To prove that these two sets are equal, we follow the usual procedure, that is we show that these two sets are subsets of each other. First we show that phi inverse phi A is a subset of AH. For that we take any element of phi inverse phi A, let x belongs to phi inverse phi A, that implies phi x equals to phi A. Now operate on both sides by inverse of phi A. We know that inverse of phi A times phi A is the identity element phi E, and from the property of group homomorphism, inverse of phi A times phi x is the phi A inverse x. So this gives us phi A inverse x equals to phi E. Now from the definition of kernel phi, we must have this element A inverse x belongs to kernel phi H, and this implies there exists some element H1 in kernel phi such that A inverse x equals to H1, and this gives us x equals to AH1, and because AH1 it belongs to AH, x belongs to AH, and this shows that phi inverse phi A is subset of AH. Next we show AH is subset of phi inverse phi A. For that consider any element in AH, let x belongs to AH. This implies x equals to AH1 for some H1 in H clearly. Then phi x equals to phi AH1, then phi x equals to phi AH1, and that is phi x equals to phi A times phi H1, and this gives us phi x equals to phi A because phi H1 is the identity element phi E, because H1 it belongs in kernel phi H. So we have x belongs to phi inverse phi A from the definition of this set. Phi x equals to phi A implies x belongs to this set. So we have AH is subset of phi inverse phi A. Now from these two relations we have phi inverse phi A equals to AH. Also in the similar manner we can prove that phi inverse phi A equals to HA. In our proof we operate inverse of phi A on the left. Now if we operate inverse of phi A on the right, we get this proof. So we have phi inverse phi A equals to AH that equals to HA. The theorem is proved.